This is Rick Felix recording for Professor Taggart's class, ET255, Intro to Digital Logic. This is an LT Spice demonstration video to create a shift register using the flip-flops and pulse input voltage sources. To start this process off, you're going to want to create a new drawing or a new draft by clicking on the new schematic. Next, we're going to plop down 4 D flip-flops. This is the typical component page when you first call it up. Integrated circuits are under digital. And the D flip-flop is the IC that we are interested in particular. As you notice, the first one you place is going to be rather large. If you use your scroll wheel on your mouse, you can zoom out. We're going to go with 4 registers for this setup. So you right click in order to stop dropping new ones. If you want something up, you can use the move mode, which is M. And if you select the circuit, it will become selectable and movable. To drop any of the tools, you can just simply right click. But if you try to drag and ensnare anything, it's actually the pan function inside the application. So next, we're going to need a couple of voltage sources. One is going to be the pre, and one is going to be the clock source. So let me explain to you how the D flip-flop works. You have the input D and an input clock. You also have 2 optional inputs that are not on all ICs, but you have the pre and the clear. So the D input will move to Q, the output, only on the leading edge of the clock source. So that's very important because the shift register wouldn't work without this theory. So what it does is on the leading edge of the clock source, if D is 0, then it puts that into Q. D is 1, it puts that into the Q output. Not Q is going to be the inverse of that. It's used in other setups. I won't be using not Q in this particular circuit. The pre is a hard set to the output. So if you put a 1 on pre, then you're going to get a 1 on Q no matter what happens. If you leave this open or set it to 0, it doesn't do it. If you force a clear, if you put a 1 on the clear, then Q will be 0. Again, that is not something we're going to be using in the circuit, but I just thought it would be worth talking. If you grab the wire tool, we're going to wire up our V1, and this is going to be how we're going to set the 1 bit in the first integrated circuit at the beginning of the simulation. V2 will need to be connected to all the clock sources because it's, well, the clock source. And that's how we're going to keep the integrated circuit in synchronization. So using the wire tool, you can just click on the XY coordinates. It will only move in one XY direction. As you see there, I just dropped it. I clicked way over here on the left and created that line anyways. And then we'll connect it to the clock input source. Now, because this is a shift register, what's going to happen is that this integrated circuit will have an output turned on, and then that will move when the clock pulses to the next integrated circuit. And then that will move on the next clock pulse. So on and so forth, down we get to the last integrated circuit. Well, now you ask, what do we do with the last output? Well, we're going to send that all the way back up to the first one. And it looks like I have messed this one up. So in order to correct that, if you go to the delete mode, it'll bring up a pair of scissors and it'll let you snip. So I just snip that connector. We're going to re-grab the wire tool, connect that properly. Output of 3 into the D input of 4. Okay. So we're all set to run the simulation, right? Right. So let's go ahead and press play. and we'll press OK. And nothing happens. That's because we didn't tell the simulation to do it. So if you press run, you either bring up this configuration analysis, or you can press the AC tool and it'll also come up with that. We're only going to configure 4 of these values here. The first one is going to be for how long the simulation runs. It just shows 30 seconds arbitrarily. It's a repeating sequence, so once you get to a certain point, it's just going to start over again and over, because that's how a shift register works. It just runs forever. So 30 seconds would be one. Then we're going to set the maximum time step. What this does is set the maximum amount of time that the simulation will run a particular scenario. So in this case, we're going to go with 1/10 of 1 millisecond for every calculation. So that's 10,000 calculations per second. Then we're also going to start the DC supply voltages at 0. We're going to force this on in order to make the simulation work better. Let's go ahead and press play. And again, no analysis request found. Wonder why that is. Well, it's because we haven't set up the voltages on anything, so there's literally nothing for the simulator to do. So let's configure the first voltage input. This is going to be a DC value with series resistance. I don't want that. What I want is a pulse input. So this is going to pulse, but I only want it to pulse once. So it's going to start at 0 volts. When the pulse is on, it's going to be 5 volts. And the time delay, so this is the first time it runs, we're going to set this to 0.45 seconds. It's kind of important. I'll explain it later. Well, it'll turn on 0.45 seconds. Our clock source is going to pulse every 1 second, with half a second being on. And it's going to have an on delay of half a second. So the amount of time that we have on this input is going to be 0.1 seconds. So it's going to be 0.5 seconds when the clock is off and 0.05 seconds when the clock is on. We're going to set the rise time to the minimum rise time, to the maximum step time, so that in one pulse of the simulator, it's going to go from 0 to 5 volts, and vice versa. And we're only going to have this cycle one time. So we'll press OK, and we'll rerun that simulation. And shoot, what happened to our settings here? So let's type these back in and hit OK. Run. Oh, now we don't have anything. What we need to do is click on one of these wires, and that will be the wire it monitors. Excellent. So we have 5 volts. It turned on one time. We're good to go. So now we have an output of 5. Nope, we have an output of 1 volt. Why? Because LT Spice defaults to using 1 volt outputs on the integrated circuits. And this just stayed on. What does our clock source do? Well, our clock is at 0. So that means the clock never pulsed. So that means that the leading edge of the clock source never happened. And so, well, the output over here is going to be 0 the whole time. So what I did was I just clicked on the output, the new output that just came up when I clicked on the output line, and its name is voltage number 4. And inside this little pop-up window, it'll tell you what the voltage is at the second. So you have the XY coordinates. And so that stayed at 0 the whole time. So that's pretty unfortunate. So looks like we have a clock problem, right? We need to set this clock source to actually pulse. So in order to do that, we right click on it and go to advanced. It's going to be a pulse input. We're going to set this to 0 and 5 volts. We're going to set the first timer to be at half a second. So after a half a second, it's going to turn on for the first time. We're going to make this move just as fast as our pulse input did. Go straight up and straight down as possible. It's going to stay on for half a second, and its period is going to be 1 second. So out of the 1 second, half of those seconds are going to be on, and the other half of the 1 seconds are going to be off. We'll leave the number of cycles blank in order to have an infinite number of cycles. Let's see, what else do we have that was bad? This naming convention is just absolutely terrible. So if you right click on a line and you go to label net, this allows you to label the line. So in this case, we're going to set this line's name to be pre. We'll place the pre right on the line, and then we'll do the output of 1, the output of 2, 3, and 4. And then we also want the clock source to have a name. In order to change the name, you just right click on it. So this is going to be output of 1, 2, output 3, 4, and this one is clock. And then the other thing that we didn't do was we needed to set the output voltage of the integrated circuit. To do that, there's a function called V high, and we will set V high to be equal to 5. So we'll copy that because we're going to need to do that on all of them. I didn't find a way to copy these settings easily from one value to another, but this program looks like it's pretty old. So features like that, I'm sure, are not available. So let's rerun our simulation. And now that it's complete, let's put our tracer on all of these lines. Well, the next problem we have is that all these outputs look like they just stack on top of each other, and it's just terrible. So if you were to double click on one of the lines, it'll make it the only one. But that still doesn't make it very good. But what we can do is if we right click over here in the plot pane, you can add additional panes. So we're going to go with 4 panes. So add plot pane below. You can use the shortcut key B. So we have 1, 2, 3, 4 outputs, and we have pre and the clock. So let's just get everything on there that we need to see. Another way to delete things, if you right click on it, delete this trace. In order to send something to the first plot, you just click into the little rectangle there, and then click on the pre line. So click in here, we'll click on the clock line, output 1, output 2, output 3, and output 4. Well, that's a little concerning because what we've got is we have the pulse input turns on V1, and then how does OP2 get turned on? Well, that means the clock source had to be in its rising time, and the input had to be on 1, and then on 2 and on. Well, that's not how actual integrated circuits work. They don't push the voltage through immediately. There is a slight delay time as the electricity flows through the integrated circuit. The simulation doesn't do that for us automatically. You actually have to give it that command. So we're going to put TD, which stands for time delay, and we're going to give it a time delay of 0.1 seconds. So I'm sure it could be smaller, but I played with it a little bit, and 0.1 seems to work very reliably for me. I'm not sure if it's just a limitation of the simulation software or not. So now that we have the time delay put in there, let's rerun the simulation one more time. And look at that. You've got the first bit being turned on by the pre-input pulse, and then that carries forward every single time that the clock source rises. So the clock source rises, turns on the first bit, falls, and then rises. When it rises, the first bit gets turned off because its input line is off, right down here at voltage 4. So that's off. So when this turns off, this one turns on because the output was on, or D was on, when the clocks went and had its rise. So on the leading edge of the rise. And as that continues to go forward, it goes all the way down to integrated circuit 4, and then back up to 1, and recycles again and again and again. So something I decided to do was I tried to set multiple registers as being on in the beginning of the circuit. So this one will have 2 on bits. So what that does is it makes these sine waves, these square sine waves, look kind of funky because the first one is on for the first cycle, and so is number 2. And the number 2 stays on because this on is being carried forward to it. When when output 2's first output got carried to output 3. And so now you're always going to have 2 that are on. So 1 and 2, then 2 and 3, 3 and 4, 4 and 1, 1 and 2, 2 and 3, so on and so forth. And you can do that again if you connect the first 3, or 3 out of the 4. And in this scenario, you have 3 on bits at all times. So you have 1, 2, and 3 are on, then 2, 3, and 4, then 3, 4, and 1, and so on and so forth. That concludes my demonstration.